This lesson deals with Supplemental Problem 314. You can find this problem in the ECE201 ebook in the Chapter 3 Supplemental Problem starting on page 15. The PSpice program has an added feature for DC sweep. It allows you to vary a resistance pretty much like we varied a voltage source in Supplemental Problem 313. The commands for doing this are listed in this yellow box. We're still going to have the name of R for a resistor, and again up to 8 characters or letters for the name. The first node will be considered the positive, the second the negative. And now we're going to add 2 more things. The model name we're going to declare on a separate line with a control command .model, and then pick a name, and then tell it that it's a resistance that we're about to vary. The next line is a sweep.dc, and then we're going to vary this resistance based on our model name, and then parentheses R with a start value, a stop value, and an increment. Let's take a Thevenin equivalent circuit and let's plot the power in the load as a function of the load. We also had some plots on page 66 of the Chapter 3 notes where we took ratios of voltages and currents with respect to the Thevenin and Norton voltage, and also some power calculations. Let's do an example to see how we're going to do this. In our example in our notes, we had a Thevenin equivalent circuit with a 12-volt source and a Thevenin resistance of 1K. I'm now going to put a resistor here, I'll call it R2. I'm going to vary it actually from 10 ohms to 100 K ohms. So I'll pass through the value where the Thevenin resistance equals the load resistance. Pick a ground as a reference. I'll pick this, and I'll call this node 1 and node 2. And so I have a title and a dot end, and I'll describe my schematic. Vn is between nodes 1 and 0 with a value of 12. R1 is between nodes 1 and 2 with a value of 1K, or 2 and 1. And then the resistor R2 is between nodes 2 and 0. And then we're going to give it the symbolic name R sub L. And the next line is .model with my name, and then telling it that it's a resistance that I'm going to be varying. And likewise with the .dc command. And so I take my symbol here for the model, R sub L, and then include parentheses. My initial value is 10 ohms, my final value is 100K. I'll take a 1 ohm increment. Let me explain what the DC command here means. The resistor R2 is being set equal to the symbol R sub L times R. That's what we had over here. And R is going to be varied from 10 ohms to 100K ohms in 1 ohm steps. So R2 then will be replaced with 1 times this value. So we could play with this and scale things if we wanted to. Let's take a look at the results on the next page. So here's a plot of the voltage across the load times the current through the load. That would be the power absorbed by the load as a function of the load resistance. And you can see here that we get a maximum, I think about 36 milliwatts at R sub L equal to R2 equal to 1K. And of course that's our maximum power transfer theorem. Then on page 66 we did some other graphs. It was plotting the voltage across the load as a function of the Thevenin voltage. In this case it'd be 12 volts. This is the curve that we had here, similar to the class notes. And you can see here as the resistance is increasing, we have more and more voltage across the load resistor. Voltage ratio is approaching 1. When we plotted the current in the load as a function of the Norton current, the Norton current would be replacing the load by a short, and then we'd have 12 volts across the 1K R1, and that would give us 12 milliamps. There's a graph here that we had similarly plotted in the chapter notes on page 66, and you can see here as the resistance goes up in value, less and less current is in that resistive load. It looks more and more like an open circuit, and most of the current's going in the other resistor in parallel with it. Also plotted the power in the load over the maximum possible power, and the maximum possible power we can get is when the load is equal to 1K. We saw in the plot above that that was 36 milliwatts, but you could also calculate that. With a voltage divider of 1/2, we'd have 6 volts across the load, so if you square that and divide by 1K, you get 36 milliwatts. And again, here's the product of the voltage and current for the load. And you can see here again the plot maximizes with a value of 1 in this ratio when R sub L equals R2 is equal to 1K. I want to make one last comment. The default x-axis in this graph is a linear scale. I changed it to a log scale, and the way you can do that is at the top of the PSpice program there's a pull-down menu that says Axis Settings. Just select the x-axis and then select log. And this is Supplemental Problem 3.14.